Hello viewers, welcome you all. In this lecture, I'm going to take up the next topics of nuclear physics, and the topics that I'm going to cover in today's lecture, they are semi-empirical mass formula, right? Semi-empirical mass formula and nuclear shell model. These are the two very important topics in nuclear physics from where usually questions are asked in the competitive exams, right? So the first of all, I will discuss about the semi-empirical mass formula. Then after I will come to the nuclear shell model. So if I talk about the semi-empirical mass formula, then you can see that it is made up of semi and empirical, right, mass formula. First of all, I want to tell you that this formula was developed by a German physicist, right, Carl Friedrich von Weizsäcker in 1935. This formula was first of all developed by this physicist who was a German physicist, Friedrich von Weizsäcker. So sometimes we also call it as a CF von Weizsäcker formula, right? CF von Weizsäcker formula, right? Now I'm coming to the name of this formula, semi-empirical. Semi-empirical means this formula is based on some theoretical predictions and some empirical or experimental verifications. So it is a combination of both the things. And what this formula gives us? This formula gives us the mass of atomic nucleus, MaZ, right? So this is our this formula. Semi-empirical means half theoretical and half experimental, right? And it is going to express the mass of the nucleus in terms of mass of proton, mass of neutron, and winding energy, right? So we know very well that the mass of the atomic nucleus can be expressed as the sum of the mass of individual protons, z time mass of proton, plus a minus z mass of neutron, then minus binding energy divided by c square. So this is the mass of atomic nucleus. We know very well, I have discussed it in the first chapter when I discussed the mass defect. We know very well when neutrons and protons join together to form the atomic nucleus, then this sum of the masses of neutron and proton is always greater than the mass of the nucleus so formed, and the difference is in winding energy. Some of the energy is utilized in winding the nucleons together inside the nucleus. So this term represents the mass corresponding to the binding energy. So if I subtract it from this term, then it will give me the mass of atomic nucleus, right? Now, according to CF von Weizsäcker, the winding energy term, this winding energy, it consists of number of contributions, right, that depend upon the different factors of atomic nucleus, right? And according to CF von Weizsäcker, these terms are volume energy term, right, symmetry energy term, right, Coulomb energy term, right, then asymmetry energy term, right, and then pairing energy term. So according to this formula, this winding energy have right 5 contributions, right? All these contributions are written here: volume energy term, surface energy term, right, and then this Coulomb energy term, asymmetry energy term, right, and pairing energy term. I think I call it as symmetry, so it was wrong, sorry for it. It is surface energy term, right, and it is Coulomb energy term, it is asymmetry energy term, and it is a pairing energy term. So I'm not going into all the details, I'm writing down the terms corresponding to this. We have to remember it. So B volume energy term is given as a B, it is equal to A B into mass number A, right? It means I can say that the volume energy term is directly proportional to the mass number, right? And here this is AB is a constant of proportionality, right? Its value is given, right? So we have to remember that BV is equal to AV into A, and we can say that volume energy term is directly proportional to the mass number, right? And this is taken as positive because this energy is responsible for holding the nucleons together inside the nucleus, right? Now I am coming to the second term. The second term is, as I told you, it is surface energy term. So if I write this surface energy term, then it is B surface, it is directly proportional to the surface area 4 pi r square. So if I put r is equal to r naught a power 1 by 3, we know very well, then this equation will become directly proportional to 4 pi, right, r naught square a power 2 by 3. Now all these things are constant, so I can merge them in one constant. So Bs will be equal to minus a power 2 by 3. Now here As is again a constant that corresponds to this surface energy, right? A is the mass number of the nucleus, and this term is taken as negative because this term has to be subtracted from the total winding energy because it reduces the stability of the nucleus. It is decreasing the stability of nucleus. That's why we are taking it as a negative. I'm not going into all details. I'm only picking up the important points. Then the third term, that is Coulomb energy term, right? This BC. So if I write down the Coulomb energy term, then B Coulomb, right? This term arises because of the mutual, repulsion of the proton present inside the nucleus, and this term is written as it is equal to minus A C Coulomb energy term constant, then Z into Z minus 1 divided by, right, a power 1 by 3. Here I told you that this is a constant, and this is the atomic number, this is mass number. So sometimes we write it as we take it Z minus 1 as Z, so I can write it as minus AC Z square a power minus 1 by 3, right? So this is the Coulomb energy term. Again it is negative because when proton repel each other, they are again reducing the stability of the nucleus, right? The next term is asymmetry energy term, right? BA. So if I write down the asymmetry energy term, right? Asymmetry means, we know very well, I have explained the nuclear stability curve in the course nuclear and particle physics. You can refer to that. We know very well that in the nuclei that for which mass number is small, for those nuclei Z is equal to n. I mean number of protons and number of neutrons are equal, but as the value of A increase, right, then the number of neutron start increasing. I have explained why they are increasing, right? Because they are increasing the stability. But when they are increased beyond a limit, right, then they also reduce the stability of the atomic nucleus, right? They also become a threat for the stability of the nucleus. So this is called asymmetry. Asymmetry means asymmetry between neutron number and proton number. Number of neutron are higher than number of protons. So if I calculate this term, I am writing it directly, right? Then B asymmetry comes out to be, right, it is equal to minus A asymmetry, right, into bracket A minus 2Z whole term square divided by A, right? This is asymmetry energy term, and I told you why this term is arising. It is arising because the heavy nuclei have a higher number of neutrons, and these neutrons are responsible for reducing the stability. That's why I am taking it as a negative, right? Now I am coming to the last term. The last term was a pairing energy term, right? Pairing energy term means B pairing, right? Pairing energy term means The nucleon inside the nucleus has the tendency to form pairs, right? And when the pairs are complete, the nucleus is extra stable. But if the nucleus have odd number of nucleons, then it is less stable. We have seen that most of the nuclei that present in nature, they are even, right? And then it comes even odd or odd even, and odd nuclei are rare in the nature. So the most stable nuclei are even, less stable are even odd even, and the rare are odd. What does it means? Even and odd even number of proton and even number of neutron. This is the meaning of it, right? So we can frame up a term according to this, right? That term I can write B pairing will be equal to plus minus delta, right? Now delta, this delta is equal to a pairing term into a power minus 3 by 4, right? And this term is plus delta for even nuclei, we have to remember, right? It is minus delta, right, for odd nuclei, right? And it is equal to 0 for either even odd or odd even. So this is the pairing energy term. So I think I have written all the terms, right, starting from the volume energy term, then surface energy term, then Coulomb energy term, then earth symmetry energy term, and then pairing energy term, right? We have to remember the expression for them, right? Now I am writing down the value of the different constants which are involved here. So first of all, the constant involved with the volume energy term, it is found by different experiments that it has value 14.1 mega electron volt. Similarly, Coulomb energy term has 0.595 mega electron volt. Surface energy term has 13 mega electron volt. Similarly, earth symmetry energy term, that is 19 mega electron volt, and pairing energy term 1.2 mega electron volt. We have to remember this because sometimes in a numerical problem you have to put these values. So we have to remember all these 5 constants: volume energy term constant, Coulomb energy term constant, surface energy term constant, earth symmetry energy term constant, and pairing energy term constant. So now by joining all these five terms, I can write down the binding energy, right? B will become equal to AB into A minus A symmetry energy constant, A power 2 by 3 minus A Coulomb energy term, right, into Z square into A power minus 1 by 3, right, then minus A symmetry energy term, right, then it was, what was the term? The term was A minus 2Z whole square, right, divided by A, right, then the next term is plus minus delta, right, and delta is I have written it here. So this is the expression for the binding energy. Sometimes numerical problems are asked from here. Now remember, this binding energy term, you will be given your situation where either the given nuclei will be either even, odd, or it is even, odd, even. But the nucleus is given, if it is given as even, odd, even, then this term will become a 0. But in case of even, it will be positive, and odd, it will be negative. Now I can write down the expression for the mass, right, of atomic nucleus. MAZ, that will be equal to Z time mass of proton plus A minus Z mass of neutrons, right, minus 1 upon C square. I am using this equation, right, equation number 1. Minus B upon C square means 1 upon C square, and inside the bracket I will have all the terms, right, corresponding to the binding energy. A, B, A minus A surface A power 2 by 3, right, minus A C Coulomb. I am writing it as it was, Z into Z minus 1, right, into A power minus 1 by 3, right, then The next term was minus uh, A symmetry, right? Then I have A minus 2Z whole square divided by A, right? Plus minus delta, right? This is the expression. Now, this is the expression for the mass of atomic nucleus in terms of different contributions, right, that are arising because of different factors of the atomic nucleus. This formula is known as a CF von Weizsäcker formula, right? As I told you in the beginning, CF von formula, or we can also say semi-empirical mass formula, right? So I told you in the beginning that I am going to develop a formula for this, right? CF von Weizsäcker formula, or a semi-empirical mass formula, right? So now I am going to discuss the applications of this semi-empirical mass formula. So the first application or implication of this semi-empirical mass formula is the condition, right, for most stable isobar, right? We know very well what is the isobar. Isobar are those nuclei which have same mass number but different atomic number, right? So if we have given A, right, given A means you are given a mass number. Now if different isobars exist for that mass number, right, then I want to know that which of the isobar will be most stable, right? So if I want to find out the condition for the stability, right, then I have to utilize the binding energy relation that was written as binding energy was AV into A minus A surface energy A power 2 by 3 we have written here, then minus sorry, yes, minus A Coulomb energy Z into Z minus 1 A power minus 1 by 3, right, minus A symmetry energy A minus 2Z whole square divided by A plus minus delta, right? This is the binding energy. Now we know very well that if the isobar or the nuclei for the given A is highly stable, right, then for that this winding energy will be maximum. And if I apply the condition of maxima for this winding energy, then obviously curly V upon curly Z, right, then A is a constant, right? A is a constant, then it should be equal to 0. This is the condition of maxima in winding energy. So if I apply this condition for this equation, then I will get the Z is equal to, I will get the atomic number of that isobar which is highly stable, most stable, and that atomic number is given as a 2 times symmetry energy, right, into A divided by, right, A Coulomb energy, right, A power 2 by 3, right, plus 4 A symmetry energy. So this is the atomic number of the most stable isobar, right? The isobar that has a highest binding energy. And I got this condition by simply applying the condition of maxima to the binding energy, right? So in this way, if I am given a numerical problem, I am given A, then I can find out the corresponding Z, value of Z, by putting the value of A, I know AC and all these things. So if I put it here, I can calculate the value of Z, right? So these type of questions are usually asked, right? Now I'm going to the second application. The application is equation of mass parabolas for isobaric nuclei. Equation of mass parabola for isobaric nuclei. Again, the same thing. Isobaric nuclei means those nuclei for which A is same but Z is different, right? So we know very well that I have written this expression for MAZ, I mean mass of atomic nucleus in terms of the mass of proton, mass of neutron, and different energy contributions. Right. Now, if I rearrange this equation, then I can write down this equation in this way. Right. If I'm not going into all that calculation, I'm simply writing it here as it will become like MAZ is equal to uh, alpha into A plus beta into Z plus gamma into Z square. Now this is the mass of the atomic nucleus. Here alpha, beta and gamma, they are constants and they are already defined. So I'm not going into all. But the thing for of importance here is, if I look at this equation, like this is equation number 3, then this equation is a quadratic equation in a Z, right? We can see here alpha A, beta Z, M A Z. A is also constant, right? Alpha, beta, gamma are constants, right? So this is a quadratic equation in a Z. So if I plot MAZ versus Z, so I should get a parabolic graphs. So I am going to plot it here. Right. You can see here. This one is Z axis, this is MA, that mass. So as I told you that if I plot this graph, MAZ versus Z, then I should get this type of graph, right? Now this graph is known as the parabolic relation for isobaric nuclei, right? How the mass of nucleus change with the change in this Z. And at the bottom, at this point, right, whatever the value of Z that I call Z naught, this will be the value that is given here, the value for the most stable isobar, right? Z is, I can say it is Z naught, right? Most stable isobar. It will lie at the bottom of this parabola, right? This point, right? And the mass corresponding to it will be the mass of most stable isobar, right? All other nuclei which are present either here or anywhere, they want to come to this side, this position. So how they can come? They can come simply by either alpha, beta negative decay or beta positive decay, because beta decay will change their Z, right? So if the nuclei is present on this side, it will undergo, sorry, I should change the color. It will undergo beta positive decay, and the nuclei is present on this side, it will get beta negative, because beta negative will increase the Z, beta positive will decrease the Z, and ultimately they will come to the bottom. And at this bottom, the winding energy will be maximum and the nucleus will be highly stable, and that will be the most stable isobar corresponding to the given value of A, right? So this is the condition for equation of mass parabola for isobaric nuclei, right? One thing that I forgot to tell you here in the beginning, that this condition, the MAZ is equal to alpha A, beta Z, gamma Z square, it has been derived from here. But the thing that we have considered here, that we have considered the case of odd A. This is Z is equal, A is equal to odd, right? A is equal to odd. This is also given. I mean odd A nuclei. This condition is for odd A nuclei, and we know very well for odd A nuclei, this term, right? This term is equal to 0. Odd A minus either even odd or sorry, odd even or even odd. So in both the cases A will be odd, right? So when A is odd, this term is equal to 0. Now when I applied this condition, I got this equation number 3, and this is the parabolic mass relation. I plotted it here, right? Then I got the condition for most stable isobar. Now if I want to go for the second condition, that is for even A. Now for even A, two possibilities are there. Either both the Z and N, they are even, or both are odd, right? Now for even, we know delta is a positive, and for odd, right, it is a negative, right? You can see here, I have written here this one. Odd it is negative, and for even it is a positive. Now when I simplify this equation, then what I will get, again I will get the same parabolic mass relation as this, but now the term that is corresponding to the pairing energy term, that won't be equal to 0. So instead of getting one parabola, we will get two parabolic mass relations. One corresponds to the I am plotting it here again. One corresponds to the delta positive, and one corresponds to the delta negative, right? You can see here again, this is Z, M, A, Z. So here you will get two relations, right? You can see here these two graphs. You will get the upper one will be for odd, right, and the lower one will be for even, right? Now all the nuclei that are present on these graphs, right, I mean here, they all have the tendency to come to this point. This is the point that corresponds to the maximum stability, and it is represented as a Z naught, just like this, right? So they want to come to this point, right? So they can do it by undergoing either beta negative decay or beta positive decay. So beta negative on this side and beta positive on this side. So they can go here like this. Ultimately they will reach here. In the same way they can come here, right? Ultimately, this upper parabola don't have any stable point, because these are odd nuclei, and we know odd nuclei are rare in nature. Even nuclei are highly stable. So that's why I am calling this point, bottom point, as the highest stability point, right? Now these are the two different cases. Now if we want to calculate that energy released in the process, or transition energy, when there is a transition from MAZ to MAZ naught, then by using these equation I can calculate the energy. So for this it will be MAZ minus MAZ naught. I mean Z is changing because of beta negative or beta positive decay. So when the transition takes place between the two isobars, then in this particular case the energy will be equal to gamma into Z minus Z naught square, right? This is for this particular case. Now we have to remember this equation, because question can be asked from here. This is for odd A nuclei, and same situation for even A nuclei. For them the condition will be MAZ minus MAZ naught. That will be again gamma into Z minus Z naught whole square, plus we will have 2 delta for odd Z, right, 0 for even Z, right? This is the required relation. So by using these two relations, I can calculate the transition energy between two states. The nucleus is going from this to this through either beta negative decay or beta positive decay, right? This we can say it is the Q value of the reaction, right? Q value, right? You can ask in any exam, calculate the Q value of the nuclear reaction when beta negative decay or beta positive decay is taking place. So these are all things about the semi-empirical mass formula and its two very important applications. Right. Now I am coming to the shell model. Nuclear shell model. Right. So we know very well that nuclear cell model has been developed to explain very strange features of atomic nuclei, and one of them is the nuclear magic numbers, right? Right. We know very well that what are magic numbers. In nuclear physics, if the number of neutron, number of proton, or both in a nucleus is equal to any of these numbers, 2, 8, 20, 50, 126, right? 2, 8, 20, 28, 50, 82, and 126. Then these nuclei are very highly stable, right? So that's why we are calling them as a magic number. Every other nuclear, right, in nature have the tendency to acquire this configuration, right? So once again, I'm repeating, if any nucleus have Z or N or both, right, equal to any of these numbers, then that nucleus is highly stable as compared to its neighbors, right? That's why we call them as a nuclear magic number. And this nuclear shell model was able to explain the these nuclear magic numbers by using the different equations of quantum mechanics, right, and classical physics as well. So it was the most successful model that was focused on explaining the stability of the magic number, although it also have other advantages, also try to explain other things like the spin and parity of different nuclei, magnetic dipole moments, quadrupole moments, right? But the main feature that it explained correctly was the nuclear magic numbers, right? Now, when a question is asked from nuclear magic nuclear cell model, then question is usually asked on you will be given a nucleus and you will be asked to write down the either spin or parity or magnetic dipole moment or quadrupole moment of that nucleus. So how we can do that? So for that we have to remember the resultant cell structure inside the nucleus, how the different cells are filled in the atomic nucleus when we add neutron and protons inside the nucleus. So we have to remember that sequence. So I'm writing it here. I have to we have to remember 1s, 1p, 1d, right, 2s, then 1f, right. This is then 2p. It is enough if you remember up to this 1s, 1p, 1d, 2s, 1f, 2p. Right. Now, we also have to remember that when I will write down the multiplicity of these different, right, S corresponds to 1 by 2, P corresponds to two factors 1 by 2 and 3 by 2, because for P L is equal to 1 and S is equal to 1 by 2. So 1 minus 1 by 2 1 by 2 and 1 plus 1 by 2 3 by 2. So that's why two possibility 3 by 2 and 1 by 2. Similarly for D you will have 5 by 2 and 3 by 2, and F it is 7 by 2 and 5 by 2, P 3 by 2 1 by 2. So we have to remember, first of all we have to remember this sequence 1s, 1p, 1d, 2s, 1f, 2p. The other thing that we have to remember, that's 2s, when I will write down the configuration or I will write down the sequence in terms of these, right, all, then 1s 1 by 2, right. This is the first term, and the multiplicity of this is 2j plus 1, that is 2 into 1 by 2 plus 1, so it will become 2. So 2 maximum nucleon can come here. Then 1p 3 by 2, now it is 4, right? Then 1p 1 by 2, right? It is 2. Now we have to remember that we are taking L plus S, earlier as compared to L minus S, right? I mean this shell will be filled first, then. So we have to remember in all, right? This will come first and L minus S will come later, right? Then after 1S, 1P, now 1D, right? So 1D, right? 5 by 2 power, it will become 6, right? Then we have to remember that the next is 1D 3 by 2, but it will become a power 4. But we have to remember that this 2s, it will come in between these two. 2s 1 by 2 power 2, right? So this is the sequence that we have to remember. 2s will come in between these two. Then 1f, right? 7 by 2 power 8, right? So this is the sequence that we have to remember. So 6, 2 plus 4, 6 plus 2, 8, 6, 14, 16, 20, 28. So up to 28, either number of proton or number of neutron, I can write down the configuration, right? So once again, I'm saying that this sequence is very, very important. 1s, 1p, 1d, 2s, 1f, 2p. First of all, we have to remember it. Then we have to remember that 2s will come in between these two, right? This is very important. And then up to 1f7 by 2, it is enough. But if you want to write next term, in case you are asked nucleus that has number atomic number greater than 28, right? Then you can write 1f7 by 2. Then again 2p3 by 2 will come first, right? Then you will get 4. Then you will get 1f5 by 2, 6. Again, this will come in between, but I think up to this point it is enough. You have to remember only one thing, that 2s will come between these two. So if you remember this sequence, 1s, 1p, 1d, 2s, 1f, 2p, and 2s will come between these two. The other thing is L plus S will label will come first, then will come L minus S. So these are some important things that we have to remember. So in this way, I can write down the nuclear configuration of any nucleus, right? Because I told you that the question is asked to write down the configuration first, and then from that configuration I can predict the spin and parity of the atomic nucleus, right? So this model was successful in explaining all these numbers due to the formation of the closed cells, just as closed shells are formed in case of atom. When the electrons enter in the atom, we know very well there is a formation of closed cells. So the same analogy works in atomic nucleus. When a cell is complete and it completes at 2, 8, 20, 28, 50, it like this. So at these positions, the nucleus becomes extra stable, right? Now I am coming to the questions which are asked from here. The first question you will be asked, that will be spin and parities, right? So we know very well spin is written as minus. First of all, I want to tell you that the spin, as far as spin is concerned, we know even nuclei have a zero spin because all the nucleons are paired, whereas even odd nuclei have a half integral spin, right? In nucleus, I have told you in nuclear physics, and that will be calculated from this configuration. I mean, whether the odd is proton or odd is a neutron, it will depend upon that. And for odd nucleus, both the nucleons are odd, so we can calculate it by using a different special formula that I will discuss here. So first of all, we have to remember that for even nuclei, the spin is equal to 0 and the parity is positive, right? 0 spin and parity positive. For even or odd even, we have to write down the configuration. For example, let's consider for beryllium 9 case, right? We know very well that it will have 4 protons plus 5 neutrons. Now we know very well that the unpaired is Obviously neutron, because it is extra here. 5, 4 are paired, fifth is extra. So I have to write down the configuration up to 5. So you can see here it is up to 6. So 1 S 1 by 2, 2, then 1 P 3 by 2, 3. So this is the configuration. This is exactly similar to the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. We write the configuration there in this way. So same way we have to write down the configuration for either neutron or proton when they enter inside the nucleus. So this rule is followed in the nuclear physics. So now this is the configuration. So you can see here the last unpaired nucleons go, and that is neutron. It goes in this cell, and for this cell L is equal to 1, right? And what is angular momentum? J, it is equal to 3 by 2, right? So I can write down that the spin is 3 by 2, right? Angular momentum is 3 by 2. And what about parity? We know very well the parity is minus 1 power L. So it is negative 1 power 1 minus 1 power 1 negative. So for this nuclei, the spin is 3 by 2 and parity is negative. So this is the way of calculating the spin and parity based on the cell model. Usually question is asked from here, right? Now it was a simple case when we have odd, even or even odd nuclei. The same logic will be applied when the proton is unpaired. Same configuration rule, it will be used. There is no difference, right? The same way of writing the configuration, we have to first of all look that which particle is unpaired, whether it is neutron or proton. Then we write down the configuration, and from that configuration I write down the spin that corresponds to J and parity corresponds to minus 1 power L. Now the situation for odd nuclei that I told you, right? If the nuclei is odd, I mean odd proton and odd neutron. Now in that case we have to calculate the spin and parity by using a formula that was given by Nordims, N-O-R-D-H-E-I-M, Nordim in 1950. We call it as Nordim's rules, right? So we have to remember this Nordim's rules. So we know very well that in this situation I have both Z and N unpaired. So in this case, first of all I will write I N plus spin of neutron plus spin of proton, right, plus L of angular momentum, quantum number of neutron plus L of proton. If it is even, right, I will find the sum of all these numbers. If it is even, then spin will be given as a modulus of spin of neutron minus spin of proton. But if it is odd, if this number is odd, then in that case it will become I is equal to IN plus IP, right? So as I told you that according to this calculation, we will find out the spin, right? First of all we will calculate the spin of neutron, spin of proton, L for neutron, L for proton. We will add them up all. Then after, if it is even, then spin of that nucleus is equal to this. If it is odd, spin is equal to this. And parity in this case is equal to minus 1 power L for neutron plus L for proton. So this is the Nordim's rules, right, that I written here. It was given by Nordim's, and we use this rule for calculating the spin and parity of odd nuclei, right? Even if nuclei have zero spin and positive parity. I am taking up one example to make it clear. You can see we have an example of 7 nitrogen 16, right? So 7 proton plus 9 neutron. Now we have to write down the configuration. If I write down the configuration, 7 proton, for proton 7, we have to look at here, 7, 2 plus 4, 6, 7 means here, right? So P1 by 2. The last nucleon is a proton is 1p 1 by 2. So it means the last proton is in this cell. So L is equal to 1 and J is equal to 1 by 2, or I can say IP, it is equal to 1 by 2, right? Similarly, if I write it for neutron, right, L for proton, then for neutron it will become 9. 9 means, you can see here, 4 to 6 plus 2 8, 9 will go here, 1d 5 by 1d 5 by 2. So you can see here, for neutron, L neutron is equal to 2, and I neutron is equal to 5 by 2. So first of all, 5 by 2 plus 1 by 2 plus 2 plus 1. I will add all these. So what I will get? I will get 6, right? 3 plus 2 plus 1. 6 is what? It is a even. So in this case, I now it is equal to modulus of I neutron minus I proton, right? Modulus. So that will give you 5 by 2 minus 1 by 2, right? It is 2. So spin of the nucleus is equal to 2, and parity, it is equal to minus 1 power 2 plus 1, in this case LP and LN1, and it is a 2 3, so it is negative, right? So spin and parity of this nucleus is a 2 negative. So this is the way of calculating it for the odd order nuclei, right? Now I am coming to the second application of cell model that can be asked. It is nuclear magnetic dipole moment. So this model also make a prediction about the magnetic dipole moment of the nuclei, right? And it assumes that the magnetic dipole moment arise only in odd A nuclei, and it arise because of the unpaired nucleon. For even nuclei, there is no magnetic dipole moment according to this shell model. And for odd A nuclei, as I told you, odd A, it gives a formula that is mu L is equal to 1 by 2 GS, right, plus I minus 1 by 2 into GL, right, whole term. Nuclear magneton, I have already explained this term, nuclear magneton. And second is situation is it is I upon I plus 1 bracket I plus 3 by 2, right, into GL minus 1 by 2 GS bracket close nuclear magneton. This is for I is equal to L plus 1 by 2, and this is I is equal to L minus 1 by 2. Now you know very well that two situation can be there, right? I can be, I means the spin of the nucleus, right? It can be L plus 1 by 2. I mean when the last nucleon is in P, and if I is equal to 3 by 2, then this rule will be applicable. And when the last nucleon is in 1 by 2, means L minus S, right? Then this rule will be applicable, right? Here GS, GL, there are a spin Z factor and a orbital Z factor, and I is the spin, as I told you, and mu1 stands for a nuclear Bohr magneton E h cut upon 2mp. We know very well that it is a unit for the measurement of magnetic dipole moments of the nucleus, right? So this is the formula that we have to remember for finding the magnetic dipole moments of odd A nucleons only. Because for even A nuclei, it is predicting zero magnetic dipole moment, right? Now I am coming to the third application. It is electric quadrupole moment Q. So shell model also make a prediction about the quadrupole moment of the atomic nuclei, and again it assumes that the quadrupole moment arise in case of odd A nuclei, when a nucleon is unpaired, and according to it, it is zero when all the nucleons are paired. I mean even nuclei in which all the nucleons are pair. I mean Z is even and N is even. If they all are even, then in that case Q is equal to 0. But if they are not even, then only we have a quadrupole moment. And according to this shell model, it is having formula minus 3 by 5 into 2i minus 1 divided by 2i plus 1 into average value of the radius square. ठीक है, here r we know very well, it is equal to r naught a power 1 by 3. So this is the formula that shell model predict for calculating the quadrupole moment. And again the same logic that according to this shell model, quadrupole moment arise only when we have unpaired nucleon, right? For paired nucleons it is equal to 0 and the nucleus is spherically symmetric. So these are some applications of the shell model that are usually asked: quadrupole moment, nuclear magnetic dipole moment, spin and parity of the nuclei, and nuclear magic numbers, right? So all these are the applications. So now this is all about these two important topics of the nuclear physics. In the coming lecture, I will take up important questions which are asked in different competitive exams based on these two topics, right? So thank you very much.